Okay, so let's see. So up to now, like I guess this week and last week, we were spending time discussing like these interpolation problems where like you were given a set of data which is finite, and then either you want the polynomial to pass through all those points, which again we did that in two different ways using like the Lagrange polynomials and the splines. The other option, which is like the one that we just finished discussing yesterday, is that you don't necessarily want the polynomial to pass through all those points, but you want it to kind of like minimize the like error in some sense, and that is kind of like like this polynomial regression that we were talking about. But in both of those cases, if you think about it, we kind of like our starting point was like a finite amount of data, like a list of numbers. We want to kind of like do now like a version of that, like in the infinite case where there's like an infinite amount of data. Okay. Um, and that will be useful for kind of like the goals of this course, which also is in part to develop numerical methods to find like integrals of functions and derivatives of functions. So I'll kind of like start talking about that topic today. Let me see if I can share my iPad. Okay. Let's see. Okay, let's see if this works now. Okay. So far, as I was saying, we had a finite number of data points. So we had a finite number and we use polynomials to kind of like interpolate this data in some way, right? And we use polynomials. Okay. Kind of like our objective now is do like an infinite version of this in some sense. So now the new goal is to do like an analogous version of this to something similar, but now for an infinite amount of data. Okay, and there are two types of infinite amounts of data you could think of. Okay, so the first type is what you would call kind of like the discrete version. Okay, and that is basically more or less what a sequence is. So the discrete version, like are sequences. So like I mean sequences, we talked a little bit about them at the beginning of of the course, but also like you studied them in Calc 2. So for example, here's like a sequence of points that you could have on the plane. You could have like an example of this would be the sequence. I don't know, let's say n comma n squared. Okay, like a very simple sequence, right? And when you think of a sequence like that, that is just like a very succinct way of like giving like an infinite num list of numbers. That is literally what a sequence is. You know, it would be, in this case, it would be, what would the numbers be? They would be 0, 0, 1, 1, 2, 4, right? 3, 9, 4, 16, and then it keeps going, right? Like 5, 25. Because if you notice, like the way I'm defining the sequence, like the y coordinate or the y value is just like the square of the x value, right? 636, and it goes on forever. Okay, so like of course, like usually you just list them maybe horizontally if you wanted to, but like from that perspective, like a sequence, um, when you think about a sequence, it is like a kind of like an infinite list um of numbers or like of data points. Now that is okay, that's nice, but usually because we want to kind of like relate our techniques to calculus, um, it is easier to kind of like work with a continuous version of this. So like the discrete version, sorry, like the continuous version of like an infinite amount of data is kind of like what a function is. So like the continuous version of this is a function. And in fact, I'll draw the graph because that's actually like the easiest way to represent, you know, a function. So if you want, if you think of a function, as just kind of like you can think of a function as its graph. That's basically actually like the kind of like the proper definition of a function is just in terms of its graph. So in a sense, like a function, it is a kind of like an infinite list of numbers or like of points if you think of them on the plane. But it's just that this list it cannot be enumerated in the same way as before because like for example you could have like 1 f of 1, but you could also then have like 0 f of 0, but also like root of 2 f of root of 2, and then also negative values, right? Like negative 3 f of negative 3, right? And then like zero point 0.5 f of zero point 0.5, and so on. And there is not like you can think, so you can kind of like think of it as kind of like storing, like a function is a way of storing an infinite amount of points. Like the only difference is that in the sequence in the previous example, you know, wait, sorry about that. In the previous example, you can really say, oh, this is the first element, this is the second element, this is the third element, this is the fourth element, the fifth element, etc., etc. So in the discrete versions, you can really just you can kind of like give a list of them. In the continuous version, you cannot really give a list of them because there's no way to kind of like say, oh, this is the first point of the function, the second point, the third point. I mean, just because, like, not to get too bogged down into details, but they are in a sense like more the points on the number line are kind of more points than the integers, even though they're kind of like both infinite. So like there are ways to kind of like give different sizes to infinity, and then the continuous version has more points in some sense. Um, I know. So if you take Math 300, like you talk a little bit about that. So all that I'm saying is that the continuous version is genuinely different from the discrete version in the sense that you cannot just kind of like count the points, but they are both versions kind of like still kind of like capture like an infinite amount of data in some sense, you see. Um, but because the continuous version involves functions, that is more related to calculus, like stuff that you know. So kind of like that will be the focus of what we'll talk today over next week. So kind of like the goal. Um, So this like, like this continuous version like interacts more nicely with derivatives and integrals. So this like interacts. So we'll focus on this one. So just to make it more precise, kind of like what we're going to be talking about for the next few days. It's kind of like if you have a function, how do you approximate a function using polynomials? That's kind of more or less what we're going to be discussing. So the goal is if you're given a function, how do you approximate it using polynomials? So you see, like if you in that sense, it's kind of like similar to what we were doing before. It's just that before you had like a finite amount of points, and then the only thing that you were asking of the polynomials was that, they it would either pass through those points or like they would be close enough to those points, which is kind of what we were doing before with like the least squares method. Here it would be kind of like you have the graph of a function, and then you want to the polynomials kind of like the graph of the polynomials to be close to the graph of the function. Like maybe that's a good way to think about it. So let me just say it like as a first approximation. Like we'll be a bit more precise later, but you would like kind of like the graph of the polynomial to be close to the graph of the function. So in some sense, the graph, the polynomial should be close. Is that making sense so far so good? Questions up to this point? So in fact, you kind of already have seen some of this stuff, uh, but maybe not presented this way. When you talked about Taylor series in Calc 2, actually. So just kind of like to give you like some like analogy that is kind of like useful to have in mind of what we're going to do. Like the Taylor series is a good you know a good comparison to have. So kind of like a good example for a Taylor series, which is like a very nice one. It's like if the function had been e to the x, right? Um, then if you remember, like e to the x has a Taylor series expansion, which in this case, the Taylor series, e to the x equals n equals 0 to infinity of x to the n over n factorial, which was 1 plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24, dot, 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 right? And, and if you can, let me see if I have GeoGebra for a second, just to like open this up. Give me 1 second. Yeah, let's go to GeoGebra for a moment. So if and that is kind of like, if you probably did this as well. If you sketch y equals e to the x, right? Let's call it f of x. If you sketch f of x equals e to the x, right? That is a graph of the exponential. And then if you let's call g or p, I'll call it p for polynomial. So if you start, if you start with the Taylor expansion, the first term, if you see like your notes is like 1, right? Okay, that is not super good approximation to the graph, right? But then you add the next term, which is x, right? And now that's how the new polynomial looks like. And then you add the next term, which is x squared over 2. Let's see, let me write it in a way that is not. Okay, and then now that's how what you would call like maybe the degree 2 Taylor polynomial would look like. And then the next term is x cubed over 6, right? When you add it up. And you see, like, as you keep adding, like, more and more terms, um, like at least near, and in the case of the exponential, it's actually like a pretty good convergence. But like, this one was, if you remember, like the terminology was kind of like a Taylor expansion about the origin. So kind of like the idea is that this is kind of like this expansion, like, or this approximation with polynomials is designed so that it works really, really well near the origin. Like, in this case, it's kind of like, you know, again, because of like the exponential function, it's a kind of like a good approximation elsewhere, but like it's kind of like the Taylor expansions are kind of like designed to so that they work really, really well at the at a particular point in question. Um, and there's all this stuff about convergence that you could get into, to just kind of like estimate, how good like the approximation is and all this stuff. But kind of like what I'm trying to say, if you look at it from this perspective, is that you have e to the x, right? And you're approximating it by polynomials. And the reason for approximating it by polynomials is that it is very easy to understand how to take derivatives of a polynomial or how to take integrals of a polynomial. Those are the kind of like the easiest things in the world that you could integrate or differentiate. So if you have like an approximation of a function in terms of polynomials, that does give you like methods for like approximating the values for integrals or like derivatives. And that's kind of like what we will kind of like start discussing like more like next week, how to use like this approximation stuff for approximating like other numerical quantities. Um, and then like just before I go back to the notes, um, if like probably I'm sure some of you, depending which classes you have taken, um, let's see. Ah, let me share this as well. And then kind of like a similar idea in spirit, in the same spirit as what I was just saying, is like the Fourier series, which again, probably many of you have heard about before. For that, there are many cute videos. I'll try to put one video on YouTube from YouTube so that you can watch it. Um, but kind of like in this case, like the idea is that you have like a function. Well, in this animation is like x over 6. Um, and you kind of like study that function on an interval. Okay. Like x over 6, because it's a line, it would kind of like go on forever. But so here what you're doing is like chopping it off. You just take the function between 0 and 6, and then you kind of like repeat it, kind of like repeat it forever. Okay. That kind of like artificially makes it into a periodic function in this case. So can you kind of like take the graph on a particular interval and you do copies of it. Okay. Um, and then, like in the case of the Fourier series, it's different from the Taylor expansion, because in the Taylor expansion, it's kind of like with polynomials. In the Fourier series, it's kind of like sines with different sines and cosines that oscillate at different frequencies. So in this case, like I can show you like I can show you some animation. So, you know, like then like, well, like I'm showing you kind of like the first steps on the Fourier series. It's kind of like this blue curve is like the one that you're obtaining. The formula is not being shown here, but it's kind of like some sort of like sums of sines and cosines of different frequencies, and then you kind of like see, you know, you kind of like see the convergence. Um, to the original graph of the function. There's some issues here, like we're at the points of discontinuity, but that's kind of like a difference, like, that's also like well studied. Um, but this is kind of like a different perspective, like, in terms of approximation, where you're using sines and cosines to like approximate the function. And this is called like a trigonometric, that for a reason that I won't get into because it involves complex numbers. This is called like trigonometric polynomials. But all that I'm saying is that with these two examples, kind of like the perspective is that, oh, okay, sines and cosines are also well understood because it's very, like, the derivatives for sines and cosines, the derivatives and integrals of sines, or like, so like, approximating a function in terms of sines and cosines is also like a very good thing that you could try to do. Okay. So kind of like what we're going to do is something similar to these two like examples, but kind of like more specific to certain purposes that we have in mind when it comes to our use will be more to kind of like approximate like the certain integrals and derivatives of the function. So like we'll kind of like use like a slightly different approximation scheme so that that works more nicely. Okay. Um, so let me just write also like another analogy, the Fourier series, just another analogy. That making sense so far so good? Before I kind of like start talking about the specific topics. Okay, so the idea is that again, you want, as I was saying, you want the graph of the polynomial to be in some sense close to the graph of the function, right? So you want to kind of like have a way to measure how you want a way to compute how close two graphs are. So that's kind of like the first thing that we should discuss. What is like a natural way to determine how close the graphs of two functions are to one another? Okay, so that's the first step of what we're going to do. So let me draw two graphs. So the first question is like, how would you measure how can you measure how close these two graphs are to one another? And I'll actually use the word distance in quotes because it literally will be some sort of distance that you're going to define. So the distance. Okay. And kind of like in many of these things, kind of like the analogy with vectors is actually very convenient. So like I should also like start there. So like, and that if you kind of like take the analogy of the vectors, um, you know, seriously, like it does give you like a good answer for what this should be. So like a simpler problem is like, how do you measure the distance between two vectors? Okay, so like here's like an easier problem. So the idea is that let me draw like the picture in 2D because like that's enough for what we want. So say like I have like a vector v1. Okay, I'll try to stick to the column vect version with vectors so that it's easier. So I have a vector v1 and I have a vector v2, right? Oh, like let me actually call them u and v because that way like the notation will be a slightly better. So like let's keep v here, but let's call the other one u actually. Yeah, like that will look better. So that the entries are just like u1 v1. Sorry, u1 u2 and v1 v2. Okay, so if the nice way to is that in order to define the distance between vectors, um, you know, if you think of the vectors kind of like starting at the origin, which is kind of like the usual convention in linear algebra, then the distance between the vectors, like it is kind of like this, like this point kind of like determine like this vector ends at some particular point on the plane, and this vector ends at another particular point on the plane, and kind of like the distance between the vectors is defined to be the distance between these 2 points. Okay, and if you remember like like Pythagoras theorem or whatever, like like let me write it like this for distance. So the way the distance between u and v is defined is just according like, and then again, this is just Pythagoras basically. I mean, it's a formula that you probably have seen even in high school, like, but it was given for points, not vectors, but it is kind of like more or less the same idea. Is that okay? So is that making sense so far so good? Like, hopefully it looks familiar. Now, kind of like the cool thing, which is kind of like maybe seems a little bit obvious in this case, is that you know, you can think of this distance as the length of the vector u minus v, right? So there is this vector u minus v, which I'll draw it. Let me draw it like starting at the origin, like so that it kind of like looks um, kind of like so that to put it in the standard presentation where it starts at the origin, but like u minus v is just like the vector that you get by subtracting the entries, right? And so this formula literally matches the length of the vector u minus v, right? So this is just the length, the magnitude, or of the vector u minus v. Is that making sense? Because again, what is u minus v? U minus 1, u minus v is u1 minus v1 and u2 minus v2, right? Like that's how you subtract the vectors. You subtract their entries, right? Um, and then then you would apply Pythagoras theorem. So that gives you like the distance, kind of like that gives you the distance of 2 points in terms of the magnitude of a vector, and kind of like the idea, and that's what I meant, like this is kind of like how we want to generalize this to the case of functions. The idea is that you want to say, okay, the distance between two functions, the idea would be to define the magnitude of a function, kind of like the length of a function, like, and then take the distance between two functions to be the magnitude of the difference of the functions. So kind of like the goal is to define a magnitude. This is usually called a norm, by the way. Define the magnitude. I'll put two vertical lines so that it's not confused with the absolute value, because it's not going to be the absolute value. So define the magnitude. So this is usually called the norm. So you define the magnitude of a function, and then and then if you somehow come up with the way to define the magnitude of a function, then you would define the distance between two functions as being the magnitude of the difference of the two functions. And then you would define. So that's kind of like the main strategy that you want to do. Is that kind of like making sense? Are there any questions up to this point? Okay, and then next question. What is the magnitude of a vector, right? So let's just go to that again. So like again, just to kind of like make the analogy stronger, let's just spend some time talking about the magnitude of a vector. So what is the magnitude of a vector? Well, again, if the vector has two entries, right? If the vector has two entries, well, let's keep writing it as a column vector. If the vector has two entries, then the magnitude is root of v1 squared plus v2 squared, right? If the vector has three entries, right? Again, this should be v1 squared plus v2 squared plus v3 squared. Okay, and as you can see, like like again, like this is kind of like hopefully like familiar formula. Like if the vector had like n entries, then the magnitude of this vector would have been v1 squared plus v2 squared plus vn squared. Okay. Okay. So far, is that making sense? Now, what's kind of like interesting about this formula, like, is that there, you can think of v1 squared plus v2 squared, or v1 squared plus v2 squared plus v3 squared, and all of these things, all of these like terms inside the square root in terms of the dot product, right? Because what would, what is v1 squared plus v2 squared? That is just the dot product of v with itself, right? If you think about it for a moment. And again, what is v1 squared plus v2 squared plus v3 squared? That is the dot product of v with itself. And likewise, for v1 squared plus v2 squared up to vn squared, that is the dot product of v with itself, right? So what I'm saying is that for a vector, the magnitude or the norm of a vector, again, like the two names are used interchangeably, the magnitude of a vector is literally the square root of the dot product of the vector with itself. So the magnitude of a vector is is that okay? Is that reasonable? So what I'm saying, so in other words, if you know how to find the dot product, you can find the magnitude, which kind of like seems a little bit silly, but it is useful to think about it from that perspective, because the dot product is an operation that's useful not just for like finding lengths, but also like determining, for example, if two vectors are perpendicular. So the dot product is like a very important operation, and is useful to notice that it is related to this magnitude business. So if you know how to find, if you know what the dot product is, you can find the magnitude. Okay, so and so the reason why I'm saying this is that because that is literally what I'm about to do next with the case of functions. So what I'm going to do now is to find a dot product between functions, which is not called the dot product, it's called like an inner product, but it's kind of like the same idea. So I'll define a dot product between functions, and once I have the dot product, then the magnitude of a function will be the square root of the dot product of the function with itself. So kind of like the goal is to define the dot product of two functions, f of x, g of x, and use that to define the magnitude. To define the magnitude for a function. Okay, and the formula is kind of like the most straightforward generalization of the dot product that you could imagine. So like let me write it right away, and then I'll start doing some examples and other things. Okay, But what is the formula? So again, what is the dot product between two vectors? The idea is that if you had two vectors like u1, well, I hate the fact that like the vectors are written always as column vectors. That takes so much space. But just to be consistent, like it doesn't matter whether I wrote them as columns or rows, like for this formula, you know. But the idea is like for the dot product, as you remember, it was u1 v1 plus u2 v2 da 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 un vn, which in the sum notation is kind of like nicer to write as like the sum from I equals 1 to n of ui vi, right? That is like the formula for the dot product between vectors. And basically what is a dot product? It's just multiply the entries, the corresponding entries, and add them up together. Okay? So I'm going to do exactly the same for functions. So I'll call it dot product, but it's really I'll use both so that like kind of like the idea sinks in more easily. So what I'm going to define right now is literally the version of a dot product, but it just happens to be called like inner product. So so the idea is that if you had two functions, f of x and g of x, basically what you're trying to do is something like this. No one writes it this way because if you write it this way, this dot that I'm putting here kind of like would get confused very easily with just regular multiplication. And this is not going to be regular multiplication. It's not like a multiplication. Like, it's not like just multiplying the functions. So like no one writes it this way. Like I'll make a comment that that's not how the way you write it. This is like the way it's written. So like never is never write it this way, but I'm doing it like for the first time just to kind of make it so this is like the correct notation because like again like there's too much risk for confusing this with like just like regular multiplication of functions. But kind of like the idea is like similar in the sense like the dot product between vectors is multiplying the entries of the function of the vector, right? So like the dot product involves multiplying the entries of the vector. So here you should multiply the entries of the function. But what are the entries of a function? They are like the values of the function. So here what you do is multiply f of x times g of x. But for which x? Well, you kind of have, that's kind of what I was saying before, like kind of like a function is kind of like an infinite list of numbers, but it varies continuously. So the only way to multiply, you kind of want to do the multiplication over all possible values of x. And the only way to do that is to kind of like integrate because like the function is kind of like a continuous version of a list. So basically what you do is integrate, the function over some interval because like let's just we'll be working functions defined on a finite interval. So define on an interval. So like like the integral goes from x equals a to x equals b. But if you kind of like compare this, it is kind of like very similar formula because like the sum, the sum gets replaced with the integral, right? That and you probably have been told multiple times already that that's how you should think about an integral. It's kind of like a continuous version of a sum. So it kind of like makes sense that you would replace the sum with an integral, and then ui vi, which are like the entries of the vector. Again, the entries of a vector are being replaced here by by the values of the function because in a sense that's kind of like what the entries of the function consists of. If you go back to you know to kind of how I was presenting here, like the function as some sort of like list. Okay. So these will be kind of like our working definition for the dot product between functions, which again is called like the inner product. And once we have that, we can kind of like find a lot of stuff about functions. Like, so this will be like a scalar. So this is like a number, like, because like it's a definite integral. It's important that it's definite here, so that, this is like a definite integral. So the answer is a scalar, just like with the regular dot product, right? Definite integral. So then the answer will be a number, like a scalar. It's just like a number. It doesn't depend on anything. It's not a function and nothing like of that sort. So f comma g is a scalar. Okay, so what I'm going to do next is kind of like give you a bunch of examples and tell you why this is a useful formula. Um, but so like, and that's what I'll focus kind of like on the rest of the class. Are there any questions so far? Okay, let's take a 5-minute break because the next part will be kind of like just doing a bunch of computations and examples. So it's like a good place to kind of like make a mini break in case also someone wants to ask me something else. Uh, uh, so the thing is that if you made it up as an indefinite integral, of course, like as a formula, you can kind of like decide that it would be I mean, you can make it whatever you want it to be, right? But then you are breaking the analogy with the dot product, because one of the most important features of the dot product, right, is that even if you start with vectors with 10,000 entries each, right, the dot product of 10,000 long vectors is like a number, right? So if you want to stick with that as being one of the key features of the dot product, you kind of like are forced to do a definite integral, if you know what I mean. Um, because otherwise you're like whenever you generalize an idea, you have to kind of like decide what you want to stick with, right? Like what concepts you want to preserve. And we have decided, like, that staying keeping with the fact that the dot product is supposed to be a scalar should be an important feature. And that's why I set it up as a definite integral. So like, you could like give a formula that involves like an indefinite integral, but then it wouldn't be recognized as like a generalization of the dot product just because it lacks that important feature, if you know what I mean. Um, it's like, so it's always like important, to be like, what is it that you really want to capture from the previous definition. And in the previous definition of the dot product, one of the things that does stand out is that it does produce a scalar no matter how big the vectors are. So again, like you could have vectors with 10 trillion entries, two vectors with 10 trillion entries each, and the answer is still like a number. So if you think of the function as kind of like just infinite number of entries, right? Like the function is kind of like infinite number of entries in a sense. So a vector with infinite number of entries. So like the answer because of that, uh, kind of like should be a number as well. So that's why you're thinking about it that way. No, but that's an important, a good question. So let's do a 5-minute break. And then like I'll start doing some examples because then this will make it a little bit more concrete, and I think that's useful. Okay, so let's say 11:25. And if you still want to ask me something in the meantime, feel free to do so. Okay, so now I think what I'll do for the rest of the class is just do a bunch of examples so that we develop some intuition about this inner product dot product business with functions. Um, and then I'll probably add some problems on the PDF list of problems, um, so that you can work on that as well over the weekend. I will send you the list of problems for the quiz. Today, I was just waiting until today's class to see what I was going to be able to cover so that that gets included on Monday's quiz as well. But let me do a few examples. So first things, again, since you want it to be a definite integral, you have to choose an interval of integration, where you want to do the integral. Uh, for most of the time, it is convenient to, it is convenient to kind of like choose that interval. Like we will, any interval, let's say, you have like let me draw the picture. if you have an interval a, b, and you have like the interval -1, 1, right? You can kind of like, if you have like an interval like a, b, and you can kind of like make a change of variables that kind of like will recenter it to be -1, 1. Because first, this interval has length 2, right? So this has length 2, and this has length b minus a. So first, like you would rescale that interval in length so that it has length 2, and then you kind of like just translate it. So basically, by doing like a change of variables, kind of like a u sub, you can always make the interval to be from -1 to 1. And that's just kind of like a useful convention, because if you open any numerical analysis textbook on the stuff that I'm going to be telling you next week, which is Legendre and Chebyshev polynomials, they kind of like have all their formulas on the interval -1 to 1. And so that's why I would just kind of like stick to this like particular interval. So that the formulas are just kind of like easier to read from any textbook. So just it's literally kind of like a u sub, like the same type of u subs that you would have done in Calc 1. You can find a u sub that kind of like turns the bounds of integration to -1, 1. So you can always make a u sub, if you had like an interval from a to b, g, g of x dx, you can kind of find like a u sub. I mean, it's a fun exercise if someone wants to try it. Like, it's just like a linear function. It's not too hard to find. Um, you can find a u sub so that it becomes like an integral from -1 to 1 of f of u g of u du. Um, Again, so like I won't kind of like worry too much about that, because all the problems that I'll give you is kind of like on the interval -1 to 1. So we will always work on -1, 1. And so because we're always going to be working on that interval, the integration will always take place between those two numbers. So the integral will be, so just to kind of like give again the formula for the dot product, which again is called like fg, that is just going to be the integral from -1 to 1 of f of x g of x dx. Again, it's kind of like what people sometimes refer to as like a normalization. It's just like, you have like a convention that you want to use. And so at least in numerical analysis, like it is like very common to do it from -1 to 1. Okay, so let me give you some examples. So, and it is just doing like integration, So it's like, computing these quantities is just as hard as doing an integral is. So for example, let's do example 1. But it kind of like has like interesting features. So like let's say f of x is x and g of x is, let's say, x cubed. Okay, and again, they are literally functions, right? They are functions. Um, so I'm going to find the dot product between these two functions, okay? Which you can write it this way if you want, like x cubed. And so kind of like the formula, the way I'm giving it is multiply them as functions and then integrate that from -1 to 1. Well, like this function is even, so if you want, you can just do it as like the integral of 2, 0 to 1 of x to the 4 dx. And okay, that one is not too bad, right? Like that is x to the 5 over 5. And like the bounds, now you can see why maybe 1 and -1 are nice bounds for certain things when you evaluate. So you get 2/5, right? So you see, it produces a scalar. That's what I'm trying to say. I think Yes, like okay, first it kind of like is convenient because well, the interval happens to be symmetric about the origin, which is can be a nice thing to have, but also that will become a little bit more clear when we talk about the Chebyshev polynomials. Um, I'm about to erase this picture because I'll do it next time. You know, if you have something like the unit circle, um, you know, the x values for the unit circle go from -1 to 1, and the thing is that some of the stuff we're going to be doing, it is very nice to frame it in terms of like the unit circle. So it's kind of like you know, and among all circles, like kind of like the unit circle is the one that makes more sense to do things with. You know what I mean? So it is because there is like some connection between this and you know trigonometry and other stuff, which will become more clear next week. And then from that perspective, like -1 to 1 is like a good like kind of like interval to like have chosen. But would that would mean an x. Uh, well, I'm not saying we're going to be working on the circle literally. Actually, in fact, like it's up like the upper hemisphere of the circle. But I kind of like was trying to explain it with the circle itself. But right, like that's a good observation. Yes, yes, yes. Like it is more like the upper hemisphere, like of the circle that plays an important role in this discussion. So like then that kind of like fixes. It's not that, but it's not that we're work you know, it's just like certain things that we'll do are related to some stuff that happens on the top half of the unit circle, basically. Uh, but there are other conventions. So, for example, in Fourier series, on a Fourier series, like when you talk about that, you're talking about functions which are periodic. And in that case, because sines and cosines are from a period 2 pi, a useful convention in the case of Fourier series is to make the integral, like, you know, the intervals from 0 to 2 pi or from -pi to pi. Those are kind of like the two main conventions in Fourier series. So like an interval of length to pi, but that is more because it's more like tailor-made for periodic functions. And, you know, for historical reasons, like sines and cosines, their periods were set up to be 2 pi. Um, you know, like a parallel universe, like, you know, you could have like define things so the sine and cosine have period one, but then you have to rescale somewhere so that, you know, like, you know, redefine the measure of radians or whatever so that the period is exactly one. And maybe that would make certain formulas like nicer to work with, you know what I mean? Uh, but yeah, I actually will explain that in more detail next week once we kind of like start talking about like the Chebyshev polynomials. For now, it's kind of like, okay, like, you know, you could have chosen any interval. Like, it does make sense to kind of like make it center about the origin. Um, and it also kind of like makes sense to, if you're going to make it center about the origin, why not from -1 to 1? Because like certain numbers are easier to evaluate at 1 and -1, you know what I mean? But obviously, like 0, 1 would also have been like a natural choice, like, you know, if you're just thinking about what is a nice interval to work with. So obviously, like, you know, it's not obvious like at this point, but you know, like next week it should become a little bit more clear, you know, like why this is like a convenient thing to do. Um, but like it's like, you know, the point of this example, like just because like we had to start somewhere, is just to show you that literally, you know, it does produce like a number in the same way in which the dot product between vectors produces a number. Um, Now here's another example. So I'm going to keep the same function f, so it's still going to be x, but I'm going to change the function g to just like x squared, let's say. And then what happens if I do the dot product? Again, dot product in quotes because no one calls it dot product. They call it inner product, you know. But what is the value of this integral now? Like it should be like a quick answer, right? Like what is the value for x cubed from -1 to 1? It's just zero, right? Is that okay? Is that making sense? So here's an example. In fact, we can draw the graphs. You know, let's say f. Let's do f. Here's f. This is a graph of f, and you know, oops. Well, it doesn't look like too much like a cubic, but maybe like this. And this is a graph of y equals x cubed, right? Um, sorry, x squared. Oops, like it had to be x squared. I drew the. I mean, you were integrating. We're integrating x cubed, but like the graphs are x and x squared. So you found two vectors. I was going to say two vectors, two functions whose inner product is zero, right? Um, so you found two functions whose inner product is zero, and so if you think of the inner product as some sort of like generalization of the dot product, right? What name did you give to vectors when their dot product was zero? Yeah, right. Like you would call them orthogonal. So just by analogy, you would call these two functions orthogonal to one another. Yes. So and literally the idea is that if somehow you could think of these as as vectors in infinite dimensions, because again the function kind of like is an infinite vector in some sense. Kind of like the idea to try to convey is that they are perpendicular in some sense of the word. You know that cannot be seen from the graph perspective because the graph perspective is in two dimensions. You have to think of the function as kind of being like an infinite vector, and from that point of view, it's kind of like there are perpendicular. But you know, like just by analogy, just to kind of keep using the same terminology, you would call them perpendicular. So in this case, we say, and this is kind of like the general definition. So you say that two functions are orthogonal if their dot product, their inner product is zero. So let's write that down as a definition. Orthogonal if their inner product is zero. Is that making sense? Here's another example. Let me just check. Sorry for a moment. Right. Okay, yes, let's do this one. Okay, here's another example of two like orthogonal functions, which is kind of like it's like the starting point of like the Fourier series, which we were not going to do, but that is where it kind of like starts. So let's say that the function had been sine of pi times x, and the other function is cosine of pi times x. So like a sine or and a cosine, they're basic. I'm multiplying them by pi just because we're working on an interval from -1 to 1, so it's kind of like again like a change of variables. So what would their dot product or inner product be? It would be like the integral from -1 to 1 of sine of pi of x times cosine of pi of x dx. Okay, and then you kind of have to remember if you wanted to integrate this, you have to remember the double like angle formula, that this is like the same as 1/2 the sine of 2 pi x dx. And that is enough to um that is kind of like enough to say that the answer is zero, because like sine is like an odd function on this interval, so that it would give you zero just because of that. Okay, and so in a sense, like kind of, and again, that's kind of like the point of like the Fourier series method, is that in some sense, like sines and cosines are perpendicular to one another. I mean, you could have used like other frequencies and like other periods. Like by frequencies, I mean periods. Like not just multiplying this by pi. You could have taken 2 pi, 3 pi, or things of that sort, and then they're still perpendicular to one another. I mean, but that is not not something that we're going to spend too much time with, because we're not doing the Fourier series stuff, but it's kind of like closer to kind of like some of the stuff I'm saying right now. So, um, is that okay so far so good? Okay, here's like a very important example that we will spend a lot more time talking about next week, but kind of like to start laying out the groundwork of what we're going to do. So there's these famous polynomials called the Legendre polynomials. So I'll kind of like write the first three ones. So again, and we will more like I'll say more about this like next week. More next week. But there's one for each degree. So the Legendre polynomial of degree 0 is just 1. The Legendre polynomial of degree 1 is just x. And the Legendre polynomial of degree 2 is 3/2 x squared minus 1/2. I'll explain, um, I'll explain some about like, why they're chosen this way in a moment. But my claim is that these three polynomials, again, everything is on the interval -1 to 1. Okay, But my claim is that these three polynomials are mutually orthogonal. Okay, so they're kind of like, if you take two at a time, they're like orthogonal to one another. Okay, so here's the claim. P0, P2, and P0, P1, and P2 are pairwise orthogonal. So what does it mean to say that they're pairwise orthogonal? That means that if you do P0 with P1, P0 with P2, right? Like they're inner products, which again, you should think about it as a proxy for saying the dot product. Um, and P1 and P2, um, then if you were to do those inner products, they should all come out to be zero. So I mean, like they're easy enough to work them out, like into, like, they don't take that much time because like polynomials are simple enough. So what is a P0 times P1 is 1 times x. So, right, you're integrating -1 to 1. You're integrating the function x from -1 to 1, right? Because it's just like multiplied by x. So that gives you 0, right? Because it's odd, like an odd function. What is P0 times P2? That again, you multiply 1 by this number, by this function, and you integrate it. So you have to integrate from -1 to 1, 3/2 x squared minus 1/2. Oh, and then actually this one does could give you something interesting, right? Because like the function is even, but like it just kind of like ends up working nicely because of the coefficients. So if you do it, when you integrate the first one, you do get what do you get? You get x cubed over 2, right? Minus 1/2 of x and -1, 1. And that will be like, like a maybe easier way to see it. uh, that why this is 0 is that this gives you the same as 1/2 x, x squared minus 1, and -1 and 1. And x squared minus 1 is 0, and -1 and 1. So that's why this gives you 0. Okay. And P1 with P2, right? What would that be? Would be you multiply x by the function, by this other function. So you get 3/2 x cubed minus 1/2 of x dx, right? And that, I mean, because it's odd, every term is odd, like gives you 0 kind of like for easier reasons as well. Is that making sense? You like the calculations? Any questions up to this point? So why is this useful? Why is it useful to say that these polynomials are orthogonal? And this is kind of like a good analogy to have with what happens with vectors in 3 dimensions. So here's like an analogy that you should keep in mind. So when you have three vectors in R3, right? Um, you have like I, J, and K, right? Like those are kind of like the canonical vectors. So you have the vector I, which is 1, 0, 0, the vector J, which is 0, 1, 0, and the vector K, which is 0, 0, 1, right? And then kind of like the idea is that if you remember like the terminology, these form a basis, or in the sense that any other vector in 3 dimensions, right? If you have any other vector in 3 dimensions, then like that vector is just like a linear combination of I, J, and K, right? Like in this case, like the linear combination is super clear because it's just X times I, right, plus Y times J plus Z times K. Right, so like again, like what this means is like I, J, K are a basis of R3. Is that okay? Is that making sense? So kind of my analogy, the analogy you should have in mind uh, is that kind of like the fact that P0, P1, and P2 are perpendicular or orthogonal in some sense means that something similar happens. Um, but instead of like working on R3, you're working on the degree 2 polynomials because at degree 2 polynomials, if you think about them, they require three parameters, Z0, Z1, and Z2, right? So you would take here like the degree 2 polynomials. So the idea is that because in order to be specified, they require three numbers. They are in a sense like a three-dimensional space. And again, if you took linear algebra, or and in fact, like in differential equations, we talk a little bit about that when you talk about linear combinations of solutions to ODE. So if you remember when you have like a linear ODE of degree 3, for example, then the space of solutions is a vector space of dimension 3. So it's kind of like similar to kind of like a similar idea. So the idea is that any polynomial of degree 2 requires three numbers to be specified, C0, C1, and C2. Um, the thing is that, you know, they are not, they are not kind of like a these three 1x and x squared, they are like kind of like a basis for this space of degree 2 polynomials, but they're not like an orthogonal basis. So kind of like the analog of ij and k are not 1x and x squared. They are p0, p1, and p2. So kind of like what plays a role of an x-axis, a y-axis, and a z-axis is the degree 0 Legendre polynomial, the degree 1 Legendre polynomial, and the degree 2 Legendre polynomial. So kind of like the way the picture would look like is kind of like here you have like an axis representing the degree 0 Legendre polynomial, another axis that represents the degree 1 Legendre polynomial, and another axis that represents the degree 2 Legendre polynomial. And kind of what we will kind of like talk in more details next week is that if you have like an orthogonal basis, which is how it's called, it is very easy to express any function as a linear combination of the basis. So if you have like a degree 2 polynomial, which kind of lives somewhere out here. So here's like your degree 2 polynomial. Then it will be super easy to write it as a linear combination of P0, P1, and P2 because like P0, P1, and P2 are perpendicular. So it's going to be C0 times P0 plus C1 times P1 plus C2 times P2. And the idea, and again, I'll like explain to you next week how to find these coefficients, C0, C1, C2. But kind of like the idea will be that for like a general function, not like a polynomial. So like next week, what we'll see is that if you have like a general function, it's kind of like the same, but then you need like all the infinite sequence of Legendre polynomials. So you kind of like would express it as a series. And this is called like the Legendre series. So it's kind of like an analog of the Fourier series. Um, but the reason for doing this is because then if you want to take a derivative, for example, if you want to integrate or take derivatives, then like it's like a great like you truncate the series, not work with the entire series. You truncate it, and then you integrate these terms, which are easier to integrate because you understand them better because they're just like uh, polynomials. So that's kind of like kind of where we are headed. And so this method with the Legendre series, there will be another one which is called the Chebyshev series, which is also very useful in practice. So there are two of the preferred methods for like approximating integrals and derivatives and other things in numerical analysis. That's why I'm kind of like spending some time right now telling you about that because it's kind of like one of the more interesting applications of like numerical analysis. Um, So if you take kind of like the idea seriously that this inner product is some sort of like dot product, there are many things that kind of like you can find like very easily by just like having like the right analogy in mind. Maybe the last thing I'll write down for today is like this formula for the magnitude of a function. Okay. Um, and again, this is called a norm. Uh, there are many notions of norm. We're not going to get into that because we're just going to use it this way. So this is but what people would refer to as a L2 norm, but there are other norms. So if you take more advanced courses, you'll learn all these variations. But we'll just kind of like do this one because it's like the most natural one to begin with. So again, the magnitude of a function. I'll put two absolute values so that to distinguish it from like just like the absolute value of the function because it's not the absolute value of a function. So kind of like the magnitude of a function. Where did I write it? Oh, the magnitude of a vector was the square root of the dot product of the vector with itself. So by analogy, the magnitude of a function would be the square root of the inner product of a function with itself. So this will be this is a formula for the magnitude of a function, which if you want to write it in more like direct terms, it's just the integral from -1 to 1 of f squared dx f square of x dx. Okay. So basically, oh, sorry, and you need to take the square root of that. So basically, you integrate the square of the function and then take square roots of what you find. And if you look at it from that perspective, it does seem very similar to Pythagoras' theorem, but just kind of like an integral version of Pythagoras' theorem. Like, that is the formula for Pythagoras' theorem, but just the integral version. So this is integral Pythagoras. So you should think about this as kind of like being the length of the function in some sense. This is, like intuitively, it would be kind of like the length of the vector. And it is good. It's a good formula because you see, this is always non-negative. So the length is always non-negative, which kind of like is something that you would also like. So it is not like a crazy definition to have. So, but again, this is kind of like a version of the length of a function. I'll put it in quotes. So let's just do an example and we'll finish it off for today because I already feel like I gave you like many useful formulas. I'll put some problems about this like on the PDF so that you can work on them. But they're like fun calculations. It's actually one of the nicer topics in all of mathematics, in my opinion, like this theory about orthogonal functions and all this stuff. It has like many useful applications. Um, like, so it's kind of like useful to learn about them. So let's find the magnitude of like I don't know, like f of x equals x, just to do something easy. So again, the magnitude of the function would be the square root of the integral of the square of the function. So you square f, in this case, the integral of x squared, I mean, it is x squared, but you have to integrate here. And so what does that give you? That gives you 2/3, right? Oh, well, let me write an extra step. So this is like x cubed over 3 evaluated at -1, 1. So yes, like that would give you 2/3, well, or root of that. So the length of the function y equals x is root of 2/3. Is that making sense, like calculation? And maybe just like as a final remark, because we are not going to really be using this, but it's still like an interesting thing to know. One thing, one nice formula, one nice property of the dot product is that when you have the dot product, you can say that the dot product is the product of the magnitudes times the cosine of the angle, right? So the cosine of the angle between two vectors is u dot v divided by length of u times length of v, right? Um, So kind of like just like if you follow this analogy, you can define the cosine of the like kind of like the angle between two functions. Like so for functions f and g, the cosine of the angle between those two functions would be then like, their dot product divided by the magnitudes. And this kind of like works. Like what you would need to know for this to work is that this is always between -1 and 1. And there's like an inequality which is very famous, the Cauchy-Schwarz inequality, that says that that does work. So like I'm just saying, like literally you can define the angle between two functions just using this formula of the inner product. So like you could compute like like in so in a sense you can talk whether two functions are at an acute angle with one another, obtuse, or 90 degrees, which is the only one that I care about, orthogonal. So that's why I'm not going to spend any more time on this, because really the dot product, the most important thing about it is like, to determine whether two vectors are perpendicular or not. Whether the angle between them is 30 degrees versus 29 degrees, that's nice, but that's not as useful. Really, perpendicularity is the main important feature of the dot product. But I just wanted you to know that, you can kind of, like literally many of the things that with vectors, you can kind of like do for functions if you have like this definition of the inner product. Like, so it is like a really good definition. It's insane, like how many things like just generalize very nicely to this case. Um, but I think, yeah, this is probably like a good place to end. So, the next week we'll kind of like start moving into the applications of what do you do with this? How do you use this for numerical analysis, which is going to be, I think, a nice part. Okay, but I'll stay here, like if someone wants to ask me anything, but if not, like I'll see you on Monday, and I'll grade the exams between today and tomorrow. So I should send you the grades by tomorrow. Yes, yes, yes.